As we do our last section in our Math 107 course, it will deal with Chapter 13, and I thought this chapter was really of particular interest, dealing with personal financial management. And some of the topics, we're going to cover the first one, the time value of money, but others, if you had time, consumer credit, truth in lending, the cost and advantages of home ownership, and then later, when you get enough money, financial investments are some very interesting topics to think about. And of course, we've taken our last test. Some of this will be included on the final exam. The time value of money. Well, one of the most common terms you're going to run into is the word interest. What does that refer to? And there's a number of definitions they're going to go over here. Well, if you borrow, let's say, $100 and have to pay it back, the bank is going to charge you a certain amount of money to use their money over that period of time. And that extra money that you have to pay when you pay off your, let's say, loan, that is the interest, which is usually given as a percentage rate. 5% interest, 2% interest, and so on. Now, the money that you borrow, the $100, this is referred to as your principal. And again, the percentage of that principal that you have to pay the bank for using their money is the rate of interest. Now, what we'll be looking at as we go through this section will be types of interest. Simple interest is one we'll be looking at first, and then later compound interest. All right, so let's take a look at simple interest. So the formula for simple interest is written up here. The interest, that is the amount of money that you're going to have to pay or that you've earned in some cases, results from the principal, the $100, times the rate, let's say 2%, times the time. And let's look at an example now. Find the simple interest paid on borrowing $5,350 for 5 months at 6% interest. Now, usually when they give your interest rate, it's per year. So we think of it as annual. But if your time is less than a year, then we have to figure out what fraction is that of a year. Here we're dealing with 5 months. So we'll see when we put it in the formula. So your principal is this, times your interest rate, and we've converted 5 months into the fraction 5/12. So you put this into your calculator, hit the enter button, and your interest is $133.75. All right, a variation of this too is like future value and present value. Now, if you take your principal, which is what you started off with, and you take the interest that you've earned on that 5-month thing, then adding these two together give you the future value. Now we can have a formula for that, and they show how it's built down below. And they're going to use the letter A, capital A, for future value. So present value plus interest equals the principal plus the principal times the rate times the time, which is your interest. And if you factor out a P from this blue part, black blue part, you get this. So we'll say in the future amount, future value, A, is equal to this over here. And we'll see that shortly. So future value for simple interest is A for future value equals your principal, and then in parentheses 1 plus RT. So again, we'll be giving you various values for these. Your role will be to accurately substitute and then accurately calculate. So let's look at an example. James took out a simple interest loan of $210 to purchase textbooks and school supplies. If the annual interest rate is 6%, and he must repay the loan after 6 months, find the future value, that is A, often referred to as the maturity value of the loan. So there's our formula, and we just carefully substitute. Our principal, 210, then 1 plus 6%, and then it's 6 months, so 6 over 12, you could put 1/2 here, but you could leave it that way since you're using your calculator. So again, I would multiply, let's say this, by 0.5 maybe to make it easier for you. Then add 1 to it, get a value here, then you would multiply it by $210. Now in MathLab, as you're doing your homework, you need to be careful because they're going to be very sensitive about what you put. If you don't actually round off to cents properly, because often it goes on a little bit, they'll count that wrong. I would give you credit for it, but they're going to count it wrong. So you need to be careful about that. Now, sometimes the future value is known, but you're wondering what would be the amount of money you'd have to put in to get that future value. So here, in this modification of our future amount formula, we're going to solve this formula for the letter P. Now all we have to do is divide both sides by what's in the parentheses here, and we get this. And again, you're going to have this formula. Solve the formula for P gives us this. So that's the one we're going to use in this next example. Finding present value for simple interest. So here we know that after 6 months we're going to have to pay this much money. So that's our future amount, our future value, which is A. So we put the $210 there. And then we're going to divide it by 1. Our rate is 2% right there. Our time is still 6 months, which you could put as 1/2 or 0.5. And if you do this calculation carefully, and you result in this. So what is this? Well, this is the amount you would have to invest or put into the bank initially, so that after a period of 6 months, it would then be worth $210. This is the formula for future value, where you know what you want to end up with, but want to find the original amount you would start with, that is, your principal. So again, these two formulas are very similar, but one solves for A above, and this one solves for P. Going on now to compound interest. How does this differ from simple interest? Well, a short little preview might be something like this. That after, let's say you have $500, and you're going to use simple interest after, let's say, 5 years. Well, this is your initial amount. You just put the 500 and figure out the simple interest. Now, for compound interest, let's say after the first year, you no longer have just 500. You now have, let's say, 520. So for the second year, it's 520. And then after the third year, your principal, because this was added, might be 540. I'm just making these up. But to show you that because it's compounded, the interest that you earn is added to your original principal, so you now have a greater amount of principal. In simple interest, they just keep using the 500. This one's a little more complicated to figure, but fortunately they have the formulas for you. Now in example 4, they're asking us to compare simple interest to compound interest. And our principal is 1,000, interest rate 2%, and time 5 years. So when we put that in our simple interest rate formula for future value, we get after 5 years it's this. But as I mentioned earlier, if you are compounding your investment, your initial balance at the first year is going to earn, let's say, $20. All right. Happened to luckily pick that. So at the second year, instead of having just 1,000 as your principal, you have 1,020. So it's a somewhat larger amount. And this continues until after the end of 5 years, compounded annually, you now end up with $1,104.08. So by compounding it annually, instead of just using simple interest, you've made an additional $4.08. And again, you might say, well, that's not too much money. Well, no, but again, once the interest rates start getting a little bit better than 2%, they've been very low. In fact, 2% is actually a good one. Then you can start, getting money from savings accounts here. Now, if we look at the chart above in example 4, we can do some other things with this formula. So we're going to do some compounding over periods other than a year, because sometimes we can compound semi-annually, which is twice a year, quarterly, which would be 4 times a year, monthly, which would be 12 times a year. And again, the more times we compound up to a certain amount, our interest that we earn is a little bit higher than just doing it once a year, because now it's 12 times a year if it's monthly, and you get a little bit more money each time. And there is a formula for that. And they go through it and bring you up to actually then the basic formula, that your principal is equal to, or I should say your future amount is equal to the principal, and then in parentheses, because you're going to multiply by your rate divided by n, which is the number of times it will be compounded during that particular year. And there's an additional formula. As you extend that beyond 1 year, and you don't need to get into all of this because it gets to be quite tedious. And then finally, we get our ending amount, which is this one right here. So again, let's analyze this. Here they're just showing you all the details of getting to this formula. That your principal, whatever that happens to be that you're starting with, and this is going to be compounded in, instead of just 1 year, those other periods of time. You have your rate. This is the number of times each year it will be compounded. So if it's semi-annually, n will be 2. If it's quarterly, n will be 4. Monthly, n will be 12. Now this m is significant because it's the product of this n down here times the time, the number of years. So we'll see that actually worked out in examples. So again, you don't need to go through all of this. This is the one that you're interested in. In fact, there is a modification of this that I'll show you. And we see it here. So m, remember, is the number of times you're going to compound during the year times the time, the number of years. So this modification is that instead of using the letter m here, they're using the nt, which is what m equals. M equals the number of times you're going to compound during the year times the time, the number of years. Okay, let's look at an example. I'll have to pull it up, but you have this available to you. Find the future value, A, the final amount on deposit, and the amount of interest earned for the following deposits. So we'll look at A first. And again, we're going to use, let's say, the first formula. Let's see if we can substitute carefully here. Now, we don't know A, but we do know the principal. This is the principal that we're going to put right there. And then the 1 is from the formula plus. Now, our rate is 4.1% that we convert to 0.041. That's what we're going to put right there. And this is compounded monthly. So this is going to be 12. There's 12 months. We're going to divide this by 12. So that's where we get this. And then since it's given us in the time frame of months, that is what we'll use for our exponent up here, our m. and that's where they get the 30 from. So again, putting this carefully into the calculator, what I would do is I'd take this divided by 12, add 1 to it, then I would go caret 30, get a value, then multiply it by this, and that would give you this value. So if we're doing some of this in class, of course we're going to pause and ask you to put that into your calculator and write this out in your notes too. So if this is the future amount and this was the original amount, the present value, then the interest earned, as we can see right down here, is $368.38. Now on your calculator you had some others, but you had to round off carefully here. As we do example B, again we're going to use the same formula. Our principal is this, that we'll put right there. The 1 is the easy part. Our rate is 3% that we convert to a decimal. We're going to do this quarterly, so that would be 4. And for a 5-year period, we can get our M here by multiplying the 4 times the years, which would give us 20. So this is going to be to the 20th power there. Again, put this divided by 4, add 1, raise it to the 20th power, times it by this, should give you this. Now that's the future value, the A. We're going to subtract the original principal from it, and we've made $2,000 or a little better in interest earned. Okay? And the little tricky part is whether you use NT or whether you use M over here. Remember, M is the product of the period of time it's going to be compounded times the number of years. Now, there are a number of formula that we're going to be using, but again, you can use your notes. That this is the one we've worked with so far. But how about if we don't know the principal, but we do know the future value? How much would we have to invest to get this amount having this detail? Well, we could solve for the letter P. And we do that simply by dividing both sides by this. So P equals then A over this, which is what this formula is. So if you know the future amount, but wanted to find out what was the original amount invested, the principal, this is the formula you'd use. And we're going to do this example now. So for example 6, we're going to find the present value for compound interest. Ashley will need $40,000 in 5 years to help pay for her college education. She's got her grandfather that's going to help here. What lump sum deposit today, that would be present value, principal, at 4%, compounded quarterly, will produce the necessary amount. So A is our 40,000. The rate is 4%, which converted in its decimal form. Since it's quarterly, N is 4. And the total number of periods will be the number of years, 5 years from now, times the period of compounding interest, 4 times a year, quarterly, gives you the 20. So I'm over-explaining that a little bit here. So what we're going to do is carefully now substitute. Well, our 4,000 goes there. Our 1 is the easy part. 4% divided by 4. and our M value is 20. Again, you're going to take this, figure it out, add 1 caret 20, and then depending how your calculator works, I would put 40,000 divided by answer, and that would give you this. So if you invested $32,781.78, now in 5 years it would be 40,000. So again, we're dealing with time value of money, which is kind of an interesting thing, a real life thing in a sense. All right, let's go on to example 7. Finding the time required to double a principal deposit. Okay. Well, again, as the statement indicates, that if you put money in at a certain interest rate, how many years would it take for that money to double? Now, one of the interesting things is we could just put it into our formula here. Here's our original principal. And if we're going to double that, that is future amount, it's going to be 2p. So our first step in solving this, we're going to divide. So we've gotten rid of the p's. Just divide the p's out here. P. So we now have this. Now, we know our rate is going to be 3%. And for our time values, let's say we're going to compound it every day. So that would be 365. But we don't know the number of years, so t is still a variable. Now, here's where you have to dig into the past, where we did logarithms, because this is an exponent. And we're going to have a nice way to get rid of that exponent using logs. And you may or may not remember this, but here's the recipe. So we then put in here log, again, base 10 of 2, log base 10 of this. Now, when we convert it to a log, we take our exponent and place it in front of the log. Okay? So now we want to solve for t. Well, how do we get t by itself here? Well, we're going to divide by this and this, which is what they've done here. And I'll raise it up. And the wonderful thing about a calculator, and hopefully we're working this right now, is that you take log 2, put that in your calculator, and then you just divide it by all of this. Just put parentheses here around this whole thing. Log of this, and you get, rounding it off, about 23 years. And of course we're ignoring leap years. 39 days, they figured that out as a proportion of a 365-day year. Okay, I don't expect that you're going to get one like this on any test or anything, but it's interesting what things that you can do. And as you vary this interest rate here, and again, 3%, you don't get that anymore. I think I recall 10% interest, it only takes 7 years or something. And that's something you could put in here and play around with. Okay, this one, not of current interest perhaps, but something to think of, You want to compare the results at age 65 for the following two retirement plans. Both plans earn 8% annual interest throughout the account building period. So, I don't know if you've ever heard of Clark Howard. He has a radio and TV show in which he gives consumer advice. And one of them is try to start saving as soon as possible. Well, let's take a look at this then. So Angie begins saving at age 20, deposits $2,000 on every birthday from age 21 to 30, so that would be 10 deposits, or a total of $20,000, and thereafter makes no additional contributions. And while we're here, Barry waits until age 30 to start saving and makes deposits of $2,000 on every birthday from age 31 to 65, so starting 10 years later, and deposits eventually $70,000. Now, what I'm going to show you, I think you're going to be surprised that you would think that the person who deposits $70,000 total would be much more, have much more in the bank or in his account than the one who only deposited $20,000. But again, it's 10 years difference. And just check this out here anyway. I know when I looked at it, I was surprised. So, and the key to all of this, by the way, is that you're getting 8%. This is, hardly anybody gets 8%. Now, in the old days, earlier times, you could get 8%, but that's almost unheard of now. But anyway, look at what happens. So, only investing for 10 years, the $20,000, by the time they're 65, they have $428,000. While the other person in Plan B, who waited until 30 to start investing, ends up with $344,000. Almost a $70,000 or so dollar difference. Wow. So here they're showing it. Take a moment to read that. Well, I think this is important then that we look at it, that the reason was because of that 8%, that the doubling time was much shorter. Had it been at a 6% rather than the 8%, then the Plan B would have overtaken by over $20,000. So again, interest rate of what you're getting. Right now it's the stock market that was doing so well, but the average mom and pop who don't have stocks, well, I won't get into the politics of it. Okay, you make up your own mind about things. So something else we often see if you deal with banks at all, and I've done it because I'm, of course, over 65. The effective annual yield. Now, you might say you're getting 5% interest, but that's simple interest. If your interest is compounded, then your effective annual yield, instead of being 5%, may be 5.2%. That is somewhat higher because of the effect of compounding that we described earlier. So they often say 5% is the interest rate, but the annual percentage yield is 5.2. Banks often give you both of those, so it helps you to do the figuring and makes you feel a little bit better about what you've done. But again, you don't see this often. Right now the interest rates are very low, and that was from 2008 because of the collapse of the housing market and all of that stuff. Well, let's go on. So for this, we're going to look at, let's say the annual rate is 2.5%, but it's compounded quarterly. So we put it into this formula where our principal, just to figure out, we're going to say is $1. That keeps our numbers small. So when we do all the computation, we get this. Well, if we subtract our original dollar from this, that is -1, we see now our annual effective rate is slightly higher than the 2.5%. It's 2.52%. That is our annual effective yield. Okay, so generalizing the formula from example 9, we end up with the formula for effective annual yield. Y stands for effective annual yield equals this, and then -1. Okay, so Yolanda wants to deposit this much into a savings account where the different banks offer different rates. So here we have a 2.08% compounded monthly. That's 12 times a year. This is 0.09, 0.01% more, but it's annual yield. That's just once a year. Or here is a lower percentage rate, but it's compounded daily. So 365. So we want to use our formula here to see which would be the best rate, because you'd be looking for your effective annual yield. So if we did our friendly one, that would end up being at actual 2.10%. The Premier, we didn't have to figure it, we already knew that was 2.09%. And the Neighborhood, even though they were doing it every day, that still only gave you 2.07%. So the best deal is 2.8%, and there's the proof. Now again, part of it is just to know the formula, where to find the formula, how to substitute into the formula to determine as you do your homework. Another term we often hear about is the word inflation. Well, this relates to your value of money and what it can purchase in goods. And through time, we say that generally there is an inflation rate and things get more expensive. For instance, when I was your age, the price of a gallon of gasoline was like 28 cents a gallon. And you've seen that it's gone up to $5 in the extreme, and right now it's, $2.10. So through time, the value of goods costing more, this is attributed to this concept of inflation. Okay? Now, the Bureau of Labor Statistics publishes a consumer price index. Consumer price index, where they kind of look at what is the cost of something and how much inflation has gone on through the various years. And you see this over here on the left. So lately, as we scroll a little bit here, we see the consumer price index has gone from a high in 1980 to 13.5, and these are percentages, to some lows here in 1986. And then let's see how far they go here. Wow, all the way to 2013. Now, notice in 2009, after the housing bubble burst and we had that recession, the consumer price index was actually negative. So let's go back and look at some more vocabulary here before we go on. Okay. Now, deflation is the opposite of inflation. So here, what we could say in terms of the gasoline, when it used to be $3 and $4 a gallon, going down to its low price of, in some states, it was actually below $2. That was a deflation. But again, we're thinking of the general consumer price index. Gasoline is only part of it. I could remember buying a new car, brand new Mercedes, for $6,000. Well, Mercedeses today are 35, 40, 50, 60, 70,000. So anyway, you got the idea. Deflation is a decrease. Now, if it extends for a brief period, this is a recession. Now, you might have heard that we had a terrible recession back in the 1930s. That was called a depression. And so I often heard the statement, if you're out of work, one man's recession might be another man's depression. Depends who it affects and the number of people that lose jobs and things like that. But again, we want to give you a general picture and understanding of vocabulary and various things. So, future value for continuous compounding. So, often this formula is used. And again, future value A is calculated by your premium, your principal. E, that value 2.78, something like that. It's in your calculator. Raised to the R, which is the rate, times the time. So let's look at example 11, keeping in mind we're going to use this formula. In 2012, the median salary for athletic trainers and exercise physiologists was this. Approximately what salary would a person in the field need in 2032 to maintain purchasing power, assuming the inflation rate were to persist at each of the following levels? So here we have the 2011 level as 3.2 and the 1980 1980 level, going back here, was 13.5%. Okay. Well, fortunately they have this worked out for us, that we're going to take A, which is the future amount. Here was 42,000 or so. E is in our calculator, and it looks like this: e to the exponent of x. And our period of time is 20 years. So future salary, if this consumer price index holds, you'd have to earn not quite double your salary. But this one is wild. I was looking at this. If this is your current salary, but it's 20 years from, again, at this rate, 0.13 times 20, and this is what blows your mind, you would have to earn almost $575,000. So this is what happens in some countries when they have this wild inflation rate, so to speak, that their currency has little value. This happened in Germany after World War I, and you see it even in like Argentina, where things are happening to their currency, and the value of bills, almost is meaningless. So again, something to consider and be aware of, and have a vocabulary to meaningfully discuss things, is sort of what we're doing here, along with the mathematics involved. Now, this is often of interest to students as well, inflation proportion. That if you had the price from a certain year and the CPI of that same year, and the price of something in another year, and that CPI for that year, you can compare things. So here they're saying the average cost of U.S. institutions for higher learning increased from this in this period to this in this period. Now, how did that relate to the actual consumer price index and what we might call the rate of inflation? Well, they've worked it out here, where they can take the average of those 2 years divided by 2 and say it's that. The average of these 2 years divided by 2 and say it's that. Set up a proportion where we just cross multiply and we get that X. This would be the amount in that future year, 3,836, but the actual cost of that year was this. So when we do that comparison, the 10,000 divided by the 4,000, we get this. And when we separate that into just subtracting 1 from it, because that would be like the current thing, there was a 178% increase beyond the normal inflation rate. So the rate for higher education, that's what I don't know if they're saying this here, but it's really gone fantastically high for students. And I'm sensitive to that. I have grandchildren that are going to be going to school, and of course you guys are going to school. So this is not just something that doesn't affect everyone. It's just true. Over the period of interest, the cost of tuition and fees of institutions of higher learning in the United States increased at a rate approximately 178% greater than the average consumer price index. So for some year, part of that we don't know what the cause is, and people have looked at that. Now, of course, in today's learning, there are many, many more devices, computers and things that are in the classrooms and schools. Salaries for teachers have gone up a little bit, but not, I don't think that much. I know for me. Anyway, well, all right. So winding this up, it says, working with quantities such as inflation, where continual fluctuations and inexactness prevail, we often develop rough rules of thumb. That is, when they used to measure things, is how long is a person's thumb. Well, the rule of thumb is, how many years does it take for something to double? And as inflation goes. Well, looking at this last formula, and we used a little bit of this before, where we had e to figuring doubling time, following it through, and here we're using natural logs. We get years to double is approximately 70 divided by the annual inflation rate. So we often refer this as the rule of 70. So let's look at an example. Estimate the years to double by the rule of 70. Estimate the years to double for an annual inflation rate of 2.3%. Well, years to double is 70 divided by 2.3. So for any of these, depending upon what your inflation rate is, you would take your inflation rate, divide it into 70, and that would give you the number of years to double. Okay, well, this wraps us up, and I don't know if we're going to have time, but there are, again, some exercises. You're going to prepare for the final. We'll do a little review in our next class, and then you have your final exam. And good luck to everyone, and get your homework completed.